No mai haere mai ki koutou te katoa. Ko Caroline Orchiston Tokawengwa. I'm the director here at the Centre for Sustainability. And it's a real pleasure to introduce our speaker for today, who's an old friend of mine from back in the day around Otago and around high school in Dunedin. So Piyush is a research scientist based at the University of Alberta in Canada. Well, actually not anymore. He's now based at the Natural Resources Centre. Is that right?
Enough.
Yeah. Natural Resources Centre? No.
Natural Resources Canada.
Natural Resources Canada. Piyush has a Rolls-Royce physics brain. He did his master's and honours degrees here at Otago, getting an A+ in his honours degree, which is just incredible. And then he went on to Victoria University to do his PhD. He moved to Canada in 2008 to take up a very prestigious postdoctoral fellowship. And he's been based at the University of Alberta and also UBC, British Columbia, off and on for the last 10 years before he joined the Natural Resources Centre. Sorry. So I'm really thrilled to hear some of his research today. This is going to be all about wildfire, numerical modelling, amazing work that he does with that brilliant mind of his. So welcome, Piyush. It's a pleasure to have you here. And as many of you will know, Piyush has been based with us at the centre on his sabbatical over a sort of a 5 or 6 month period, which is due to end, I think, in April.
Yeah, for sure.
So we'll be seeing him off again shortly. Yeah.
All right, well, thank you, Caroline. It's the nicest introduction I've ever had. And I didn't even remember all that stuff. So good to have a wee update. Yeah. Okay, yeah. So as Caroline mentioned, there was someone trying to get in, but as Caroline mentioned, I'm actually working with the Canadian Forest Service, which is a branch of Natural Resources Canada. So our mandate is basically to look at the sustainability and health of Canadian forests. And a big part of that is looking at natural disturbances, and probably the major natural disturbance in Canadian forests is wildfires. So that's what I do. And there's like 20 or 30 of us in the group that do that. That's a script.
Do you want to
The weird thing is because I'm sharing this, I can do that.
Oh no, here we go. So yeah, if you can click that one.
Oh, yeah. Yeah. So I'll just start by giving a little bit of an overview of the sort of fire activity that we see in North America, and sort of where we see fire, how much fire we see, and what are the causes and drivers of that fire. And then I'll go a little bit more into the sort of research that I do myself and others do in our group. So the left-hand map shows basically the forest in North America. So that large swath that goes from Alaska all the way down to the eastern seaboard is the North American boreal forest. And it's a very active region of fire, as you can see on the right-hand plot, which shows essentially a climatology of burned area from satellite photos. And then obviously there's a lot of fire in Western US as well, you know, California, Oregon. It's all over the news all the time. We hear about it every year. Essentially, there's a lot of fire in North America. And you can't talk about fire without talking about the potential ignition sources. And the two main ignition sources are lightning and human cause, so which correlates with population density. So you see there's a lightning density plot on the left. That's again a climatology from our lightning detection networks. And you see there's a lot of lightning over North America, and it tends to peter out the further north you go. But there's still enough lightning, even at those high latitudes, to start fires. And population density, obviously Canada, you know, is well known for being quite sparsely populated, and then as you go further south, particularly in the east of the US, there's a very large population base. So there's a lot of fires caused by human activity. Not what you always think. It could be you know, someone driving their recreation vehicle and just a little spark from the tire or whatever hitting a bit of grass starts a fire. So not necessarily people doing things on purpose. Or it could be power lines that fall down through the strong wind events that may start fires. There's all sorts of things. So those are all classified as human-caused fires. So just I might not read all the statistics on here, but it's useful to get bit of context about how fire regimes are different in the United States than they are in Canada. So in the United States, there's 73,000 fires a year, and most of those are human caused, and 2.8 million hectares on average burns per year. Whereas in Canada, we have much fewer fires, but they tend to be larger fires because they're often allowed to burn, become quite large. So we have 2.1 million hectares burned per average on, and 85% of those fires are lightning caused. And I looked it up the other day. The area of the Otago region works out to be 3.1 million hectares. So essentially of the order of the whole area of Otago is burning on average every year in North, and more than that actually, almost double that in North America. So it's a lot of fire. And the other thing I just want to point out is that there's quite a clear signal. I think the United States, the area burned is increasing, and that's been attributed to climate change in many, many studies. In Canada, the signal is also strong, although there is, I don't think I'm talking to it. In Canada, the signal is also strong, but there is a weekly increasing trend in area burn. So. Now, fire is not always a bad thing, particularly in North American ecosystems. Fire is a natural part of the ecosystem. And a lot of trees and plants have adapted to be resilient to fire. And in fact, some species even require fire to propagate. So there's those top two pictures kind of show you some pine seedlings starting after a fire being I'm sure what the word is because I'm not a fire ecologist, but there's a technical term for it. You know, they're just growing again. We'll go with that. And then, you know, even if the trees don't succeed, you can have plenty of plants which thrive in that soil after a wildfire goes through. So, and that's important for the ecosystem because it's, you know, can provide nutrients to animals. So in fire science, we really like triangles. So there's a whole bunch of triangles here. And this is where the different scales of fire science sort of come in. So at the very basic scale, you know, what is fire itself? You know, you need oxygen, heat, and fuel. So you're talking about, you know, when you go and set your own campfire or whatever, that's what, you know, those are the essential ingredients. And then we go to the scale of individual wildfires. And there we tend to talk more about weather, and topography is a driving factor. Like if a fire is running uphill versus going down or whatever, the dynamics are different. And then again, fuel. So what's on the ground to burn. And then at much larger and longer timescales, what we call wildfire regimes, we talk about climate. We talk about ignition sources. So they may be changing as time goes on. There may be more human ignitions for some reason or less. There may be more lightning. It's postulated under climate change, there'll be more lightning in certain regions. And there may be even vegetation changes over long enough periods of time because of land use, changes in land use or forestry or things like that. So they can all inform wildfire regimes. Now, my specialty of research is fire weather, and that's partly accidental because the person who hired me first to start working in fire is a well-known fire meteorologist. So that's where most of my research lies. So it's worth just talking a little bit about different scales of fire weather. So obviously there's the micro scale, there's at the individual tree or stands of trees. You can have microclimates. Just because of the local topography and trees are around, you know, as you above the trees or, you know, getting under the trees, the winds can be different. Everyone knows these sorts of things. And then you can go up to the mesoscale, which is kind of more of the range which we get our weather forecasting. You know, is it going to be raining Dunedin this afternoon, so forth. And then you can go to the much larger scale, so the synoptic scale, thousands of kilometers, looking at large-scale atmospheric patterns, things like the jet stream, Rossby waves, polar vortex. And those things can cascade down and affect the weather at the local scale, which will then affect whether we have conditions conducive to fires. So I kind of look at all of those scales to a certain degree, not so much the micro scale. Now it's worth mentioning the system that we use in Canada to rate fire danger. It's called the Canadian Forest Fire Danger Rating System. And part of that is what's called the Fire Weather Index. So what that basically is a proxy for fuel moisture. So it has a whole bunch of surface weather variables: temperature, relative humidity, wind, and precipitation. And they go in and this calculator churns through and sort of just keeps track of how moist different levels of the forest floor are. And that is kind of a proxy for how flammable the forest is. And there's historical reasons and also convenience reasons why it's done that way, because it's easy to sample the forest floor. It's harder to sample actual moisture of growing plants. So everything's been calibrated to correlate with different metrics of fire danger. So yeah, and I'll be mentioning some of these fire weather indices, in particular the initial spread index and the fire weather index later on. But those are just, you can just think of them as proxies for like the potential for a fire to spread or how intense the fire might be based on what the weather is doing. So I think it's useful to actually look at a fire, you know, to get a sense of what we're talking about. Wonder if there we go. So this was a McMillan fire, 2019 in Alberta, and it was a very large fire, over 200,000 hectares. You know, so that's, again, I looked up some figures, and that's about over a quarter of the area of the Wellington region, the greater Wellington region it is. So it's a big fire. And we sometimes get those really big fires in spring in Alberta. So I've got an arrow there because there's multiple fires burning at the same time, but that's the one I'm pointing to there is the McMillan fire, and you can see there's a very large smoke plume. I believe that year the smoke was so bad that the street lights came on at lunchtime in the city of Alberta. So yeah, it's a big fire, and we have a lot of really good data now. We have satellite products that are able to let us recreate these so-called fire histories of what day, what part of the fire burned. So that's what you're seeing there on the left is basically a fire progression map recreated from satellite data. And we can use that sort of data to help us understand how fire spread and how weather drives fire spread. So yeah, this is probably a bad idea to put 9 plots on a single slide, but I've done it anyway. Lucky for you, I broke it up into left and right because earlier it was just one big vertical. So anyway, the top left-hand plot is the area burned as a function of day of year. Okay, so that's really the fire activity that we're interested in comparing to what the weather is doing. And the second plot is radial spread. So you take the area burned, you make some geometric approximations about the fire, and then we look at, you know, how far the fire front has moved in one direction rather than the area burned. And that's very important. Fire managers want to know how high that is, because if it's a very fast fire spread, it makes it very difficult to contain the fire. So that's a quantity that they're really interested in knowing. And then there's quite a few different fire weather indices that we're looking at. So the FWI and ISI I mentioned earlier. The last one there is the VPD, which is the vapor pressure deficit, and that's a measure of how dry the atmosphere is. So you can see there's basically, and those red lines, sorry, I should say, are what we call spread days. So those are days where the fire spread above a certain threshold of linear distance, and those are fires that we say they're spreading uncontrolled, and it's very difficult for fire managers or firefighters to actually put that fire out or suppress it. So those are very active fire days, and you can see it correlates quite strongly with those fire weather metrics and most of the metrics here. There's a couple more metrics I've thrown in here. I won't talk too much about it, but it's not just surface weather.
I just shit myself.
Not just surface weather we're interested in. We're also interested in the vertical profile of the atmosphere and whether it's
Shut up, bro. I don't think anyone asked.
Sorry, could we ask those online to please mute themselves? Thank you. I should have said that before. Sorry.
Piyush, what are the units? So it's spreading at 6,000 somethings a day.
That's a good question.
Meters.
So we meters, yeah,
Meters.
Yeah.
So 6 kilometers a day.
yeah, quite a lot.
Yeah.
Yeah, this is the example I gave you is not perhaps typical fire. This is a very, very large fire. Yeah, so, yeah, and these instability indices tell you a bit about the convective environment above a fire. So fires can create sort of atmospheric conditions and the heat of the fire itself cause the fire to basically act like a chimney and just eject a lot of energy vertically. And what happens then is you get these sort of downdrafts of air coming in to fill that low pressure that's left behind, and that feeds the fire again. So it can sort of feed on itself, and you get this very erratic, very dangerous fire activity. And that's what's called a plume-driven fire. So I won't go into the details of it, but basically the first bunch of spread days here were basically wind-driven, and the second lot were more plume-driven. So what you can do is you can look at how these fire weather metrics just statistically vary with either non-fire days. So fire days, that is days where you have burning, but it's not that so-called spread day, those dangerous spread day events, and then spread days. And the main thing I just wanted you to get out of this slide is that when you look at the 90th or 95th percentile of each value of each different variable, that's basically where these spread day events sit, right? So when you look at the higher percentiles of FWI, for example, you're more likely to get a spread day or a potential spread day. And later on, I'm going to come back to these extreme fire weather values, and we're going to talk about it in the context of climate change. So that's just what I wanted to get out of that slide there. So I'm just going to come back to this slide because I now want to focus. I've talked a bit more about the micro mesoscale, the scale of an individual fire, and now I want to talk more about the very large scale. And the reason it's useful to talk about large scale weather patterns. Oh, raised hand.
Would they like to ask a question now, or would they like to wait till the end? Someone's raised their hand.
Should I ask?
You could ask.
Was there a question, or would you like to wait till the end?
Hi guys, just Gemma here. For security, I actually disabled a lot of things as we had someone interrupt before. So I'd recommend we leave questions till the end if that's okay.
Great.
Sure.
Thank you.
Thanks.
Thank you.
Yeah, so it's useful to look at large scale atmospheric patterns because large scale atmospheric patterns, quite often the dynamical evolution of the atmosphere is what can lead to extreme weather events. And that includes weather patterns which are conducive to fire. But the other reason is that it's not to scale weather, it's much easier to predict in weather models. So if we can understand what large scale patterns are going to lead to extreme fire weather conditions, that's going to help us predict these things going forward. So in the Northern Hemisphere, in the mid-latitudes, which is around 30 to 60 degrees north, the jet stream is very important for sort of dictating the various weather patterns. A lot of the storms, anyone that's lived in North America will be aware of this. So we decided to do a study looking at how the various jet stream patterns correlate with these spread day events. So this here in these plots, the purple or pink, I'm not sure what color those are, circles are essentially spread day events on that particular day. This is a couple of different days showing examples. And then you can see superimposed on the jet stream pattern on the left, and on the right, we're looking at geopotential height anomalies, which are basically used to look at blocking. So in the upper atmosphere, what's the pressure? That's a measure of like whether we have a high pressure system there or not. Or, heat wave is another way of thinking about it. So you can see that there's for example, on the left hand, the top example, you have a very strong ridge, which is equivalent to having atmospheric blocking under that ridge. And so there's a lot of fire events in that vicinity. And in the bottom configuration, we have what's called a double jet. The jet doesn't have to be a single jet, it can fragment, and sometimes when it fragments and there are two strong jets, you get actually blocking in between. So what I mean by atmospheric blocking is that usually you have weather patterns just moving through from west to east, going with the flow of the jet stream. But when you get blocking, basically weather systems stall. And sometimes what this means is you can have an area of high pressure which just sits there for several days. And that's basically a heat wave. And those conditions obviously are conducive to having very hot, dry, windy, dry weather. And when those break down, quite often there's a front that goes through that can have lightning and can have very strong winds. And so you can have a lot of fire activity because you've dried out all the fuels and then you have the conditions for fires to start and spread very quickly after that. So, yeah, so we sort of did a more, I should keep a track of the time, I do tend to go on. So we did a widespread study using satellite data. So looking at fires between 2002 and 2016. So that map on the left shows you all the spread day events that were identified in North America for large fires. So that is fires which are greater than 5,000 hectares. And we just had to choose a large number because if you choose too small a number for the size of the fire, you just don't see them in the satellite data. And then we looked at the jet stream pattern. So this middle so-called composite analysis, basically it's the average pattern that you see around a fire event. And this is just the V component, which is the north-south component, the so-called meridional component of the winds at the high altitudes. And I guess the red blob on the left of the fire event, so to the left of the zero cross, just means you have winds going northerly, and to the blue blob to the east means the winds are going southerly. So that's your ridge, right? That's the winds going up and over, and that's corroborated by the geopotential heights where you get this high pressure area building in the middle of the centered around the fire spread. So basically, I mean, there was nothing overly new about the study, but it did confirm the sort of weather patterns in North America, at least, that we expect will lead to strong fire spread events. And the other reason people are really interested in the jet stream is maybe several of you have read articles in the media about the potential changes in the jet stream because of climate change. So the idea is that because of Arctic amplification, so the Arctic is warming at 3 times the rate of the rest of the globe, that weakens this so-called poleward temperature gradient that we normally have, that, you know, obviously at the tropics, it's warmer than at the polar regions. If that gradient in temperature weakens, the jet stream can become much wavier. And if it becomes much wavier, you can have these patterns where, you know, polar air comes down south, but conversely, where you have warm air from the tropics going further north. And you have more of those patterns, you're going to get more extreme weather. So that's the idea. But I've just put up 2 papers there, but there are hundreds of papers on this topic. The jury is out. We don't know whether that is what climate change is causing. But that is just some motivation for looking at these things. So another study that we did was looking at these geopotential heights to look at basically heat wave type events. So I think everyone will be familiar with the heat dome, the Pacific Northwest heat dome that occurred in June, July 2021. It was a huge, basically blocking ridge. And that purple dot there in British Columbia is the town of Lytton. And the town of Lytton experienced, I think on the 28th of June, around that time, had a temperature of 49.6 degrees, which is a record temperature for North America. Hundreds of people died during the heat dome, particularly elderly people. Fires were started across North America. Temperature records were broken all over the place. It was a huge event. It was also a very sizable event, and it moved from the west to the east, starting fires. So there's actually a video here. So that blue outline is tracking the heat wave. So that's an algorithm which we developed. And those little triangles are basically fires starting. And the red triangles are the large fires, about 200 hectares. So you can see that it tracked from the west to the east. And either during the heat dome or just after? Because that was the effect I talked about, that you dry out the fuels and then after the heat waves moved on, you may have conditions for the fires to actually start. You can sort of see that it tracks quite well with the heat dome. So anyway, you can put that particular heat dome event in the context of other such events, going back just through the weather data. So the particular data set we used, reanalysis, we went back to 1979. And that blue line shows the maximum sized event for every year in that study region. And you can see how 2021 was a much, much stronger event than the other, than any of the other years in that particular record in that region. So there have been some studies done trying to estimate the return period. So I think many of us are probably familiar with the idea of return periods, particularly flooding and various things like that. So the two papers that I've seen, there's estimates of 200 years was a lower estimate, and over 1,000 years a higher estimate. So this was a very extreme event. I guess that's what I want to emphasize there. And we also did, this is some work in progress that we have in review right now. So we also did what's called a light attribution. So the idea is, how much more likely was this event because of climate change? And you can play a little game, or what you do is you detrend. So you get rid of the climate signal from the geopotential heights and you redo the calculation. And then what you see is that blue curve. So the red one was the observed curve. Sorry, I switched colors on you just to keep you on your toes. The red one is what was actually observed, and the blue one is if you take that climate change trend out and you redo all the calculations. And what actually you find is that if we define the strength of the event as the amplitude, so that's how much that geopotential anomaly is, times the size and times the duration, we find that it was 71% stronger because of that climate change, the anthropogenic signal being included versus when it was removed. And you can sort of delve into it a little bit deeper by looking at the time series of the observed event, which is in black, versus the detrended event, which is that dashed line. And so it's obviously it lasted longer and it was stronger. Some other impacts of 2021, record-breaking fire weather. So what those 4 panels are showing are different fire weather indices, and it's showing the record values that were occurred in 2021 only, taking data from 1979 to 2021. So anything that's colored in there is a record broken in 2021, and anything with the black outline around it was a record broken during that heatwave event, that single heatwave event. So you can see, for example, maximum daily temperature, which is at the top left, records were broken over most of Western Canada and a lot of the Pacific Northwest in the United States. So it was an amazing event. In Edmonton, where I live, it was 38 degrees and we got off lightly. So yeah. Another thing we can do is we can look at the area burned as a function of day of year. And those curves, those colored curves, are essentially how much burned within that single heat dome event versus the gray curve, which is for the entire year. So we can sort of attribute 21% to burning within the heat dome. But then if we say we give ourselves another 5 days, we include fires that burn 5 days after the heat dome left, or 10 days, the number goes up to 34%. And that's that blue curve there. Some other impacts of 2021. I like to talk about 2021 because there's lots of stuff to talk about, I guess. From a fire management perspective, we have these alert levels called preparedness levels. So they go from 1 to 5. So essentially 1 is like there's very little fire going on. Any fire that's going on can be addressed locally. 2 is kind of the same, as a little more fire activity, but local fire managers can deal with what they got. 3, it's starting to be more widespread fire. You might have to start asking for resources from different places. 4 is you will have to ask for resources from neighboring provinces or other parts of the country. 5 is very extreme. You may be asking for firefighters to come from Australia or New Zealand to help you fight your fires because you just don't have a choice. So the thing to point out there is that those are level 4 and level 5 days in that stacked fire plot, and you can see 2021 has the most number of those level 4 and level 5 days. So fire management was under extreme strain for a very large part of the fire season in 2020. The middle plot shows smoke. And so basically that's aerosol optical depth, which is a kind of a proxy. It's often used for smoke because it can be satellite viewed. It can be measured directly by satellite. And yeah, so we came up with some estimates that between 20 and 68 million people were exposed to smoke because of that heat dome event, because of the fires caused by the heat dome event in July 2021. I believe in New York City had the worst air quality in the world for one day because a lot of that track smokes west to east. And finally, this is a wee little video. It's a very, very short video, actually, showing the Sparks Lake fire. What is interesting about that is that when you have an intense enough smoke column and enough heat that goes vertically, that chimney effect that I talked about, it can go very high into the atmosphere, to the upper troposphere or even stratosphere, and it can condense moisture in the atmosphere and create a thundercloud. So this is called a pyrocumulonimbus. So it's basically a fire-generated thundercloud. And this particular one was so large that there were over 50,000 lightning strikes in an 8-hour period, cloud to ground. And some of those lightning strikes then went on to start new fires. So this is extreme fire behavior. And you do see it in other parts of the world. Australia has it, but this is probably one of the largest ones on record.
Do you ever get heavy downpours from those pyrocumulus clouds?
Yeah, you do.
Enough to put out the fire?
Yeah, yeah, you can. To put out the fire, I don't know. It's hard to resolve those things.
Yeah.
Yeah. So just to briefly talk about climate change. We looked at those. Remember, I was talking about those extreme values of fire weather metrics. So we looked at some of those, the FWI, ISI, and the vapor pressure deficit. So I think a well-cited number is the last 10 years contain 8 of the hottest years on record. So the colors there are basically the global land surface temperature. And then the height of the bars are the anomalies in those extreme fire weather metrics. So you can see that globally, it's basically tracking with temperatures. The more intense temperatures we're seeing, the more intense fire weather we're seeing. And in fact, we found that between between a quarter to half of the world's burnable biomass was experiencing positive significant trends in fire weather metrics, depending on which metric you look at. And in North America, I'm just zooming in on that here, it's mostly in that area where we are seeing a lot of fire. So I think there's a pretty strong argument to be made that climate change is changing fire regimes in North America. Not so clear maybe in other parts of North America, but definitely in the West. I've started recently, one of my colleagues, Kendrick Brown, is in Victoria. He is a paleo scientist. He's a paleo fire scientist. So I've started working with him. This is his slide. So I'm going to talk to it, but I just find it really fascinating. So 5 million years ago, global carbon dioxide concentrations were a little bit higher than they are today. Right? And if we look at this Ellesmere Island, which is in the Canadian Arctic Islands, and there's a little town there, Eureka. The mean summer temperature 5 million years ago was 15.4 degrees. And this is an artist's reconstruction, which basically shows there was a very active ecosystem. There were lots of animals. There's boreal forest. They had forest fires that can get the soil from these different types of proxies, charcoal, pollen, bottles, and so forth. They can sort of reconstruct what it was like. Today, with CO2 levels almost the same, the summer temperature is 4.1 degrees, and it's basically barren. It's the photo of that region. It's basically barren, but you know, you don't know. Obviously, it takes time for the climate system and for the ecosystems to catch up with the climate, what the climate's doing, and it may never revert to something like that. But for me, I just find it fascinating that, you know, under similar atmospheric conditions, how different it was that long ago. So. This is my final topic. I guess I'm doing all right for time. So most of the stuff I've presented so far is, you know, kind of research on historical fires. But there is a lot of research also being done on trying to address fire management. So this chart here, this is from some of my colleagues in Canada, but basically it's showing the sort of fire management activities that occur at different scales, different spatial scales and different temporal scales. And this is Ontario, focused on Ontario, but I think a lot of it can translate to different areas. So essentially there's, you know, at the smaller, more immediate scales, there's, you know, needing to know information right now about what the fire is doing so we can, you know, send people out to the right spots and we can, you know, fly our planes in the right regions and so forth. But then at the longer scales, the daily preparedness, you've got to like allocate who you send out to a particular fire on that day, how many aircraft you might send out. You've got to, you know, maybe be able to alert the public if there's an evacuation order that needs to be issued and so forth. Multi-day preparedness, that's when we start getting into this idea of maybe you need to send resources from one fire agency in one province to another. And then there's like even just seasonal things like, you know, at the beginning of the season, how many people do we hire, right? And how many aircraft, because everything's on a contract, right? So it's a lot of money. It's been hundreds of millions of dollars every year in Canada, for example. So that sort of informs the different forecasts for the different, time periods for weather forecasting. Because if you want to predict fire danger, there's different types of weather models you can use. So you can use weather models which are short range, 1 to 3 day, and that'll help with, you know, the immediate response on fires. And there's the 4 to 10 days, and that's around more resource allocation. And then you get into the 10 to 30 day, which is also called sub-seasonal forecasting, and beyond 30 days. And I think everyone can appreciate that as you move from the left to the right, the skill of those models generally goes down, right? It's very hard to do sub-seasonal or seasonal predictions of what the weather is going to be doing. But if you can get any sort of incremental gain from doing that, you can save $5 million because you put your resources, you know, in a better way. It's still worth trying to do that. So we've been working on some of those things, and it seems like I'm randomly jumping topics again. I'll come back. So machine learning, we did a review of machine learning in fire science, and it's exploding like it is in most fields. We also looked at what sort of applications machine learning are being used for, and one of the things it's being used for many things in fire science. But one of the things I think it's being underutilized for is in the area of prediction or forecasting. So can we predict how the fire is going to grow, or can we predict fire weather conditions into the future, right? So that's something we've been trying to address in some studies. Here's an example of one study that just we engaged with the Alberta Machine Intelligence Institute. I hope I've got that right. They're machine learning experts attached to the University of Alberta. We tried to develop an early warning system based on basically trying to predict extreme values of FWI using these large-scale atmospheric patterns. And they came up with this hybrid deep learning model. I don't understand all of it, but the two basic things are this so-called attention mechanism for knowing what part of the weather pattern spatially to look at. And then there's this long short-term memory component, which is like a way of doing time series forecasting. So it's basically got a memory that sort of loops back and remembers what's happened in the past and then learns what things are going to happen in the future. So they developed this model, and the idea is that can we forecast the extremes in fire weather 1 to 10 days in advance? And so the model shows some skill, but unfortunately we couldn't get it quite far enough. So there's still a bit of work that we have to do on that. We're hopeful that it may, or at least get a publication out of it, but hopefully it's useful for someone at some point. So that's all I've got for today. So if there's any questions, I'm happy to answer them.
Well, thank you so much, Piyush. That was beautifully described. Your science communication skills are right up there. I love it when people use words like blob and wavy lines to describe data. That's awesome. It really helps my brain. So I'd like to invite questions from those online. Thanks for joining us via Zoom. And just raise your hand if you've got any questions, and you can either speak to it or you could put it in the chat. And if we have any questions from the room, if you ask a question, then I'll ask Piyush to just reword the question so that those online can hear it. So does anyone have any questions? I have a question behind me, do I? Is there a question? Raised hand. Raised hand might have been a relic of earlier, I'm not sure.
No, I just
Did it?
Oh, here it
Okay.
is.
Marwan, would you like to ask a question? Just unmute yourself and go ahead.
Hi, they won't be able to unmute themselves. I'll just need to use the chat to ask their question.
Okay, well, while the chat's happening, I'd like to ask a question,
Sure.
which is around that heat dome video that you showed us. And it looked to me as though, am I right in thinking the fires that ignited around that heat dome were actually around the periphery, and is that a wind function? Because a lot of them weren't actually happening in the hottest part of that heat dome. They seem to happen around the outside. Is that what I'm observing, or not?
That's what people think.
Mm.
The problem is that sorry, I'll get back to it. They're very hard for the weather models to resolve the winds that actually drive fires at the surface.
Right.
So that's one of the big issues actually in sort of studying fire weather, is that anecdotally, of course, the fire managers who are out there, or the firefighters, will say, oh yeah, it's really strong winds, and then we look at the models and we don't see them.
Right. So internal, that sort of localized wind effect around fires.
So in British Columbia that year, because the fire manager was telling me this, there was a lot of so-called downslope winds. So in the evening, you see it in Mount Cargill here.
Yeah.
The winds come down the slope, right, in the evening as it cools down. And those, if there's already a fire there, that drives the spread of that fire, but it's very hard for models to pick that up.
What the natural sort of happens about the fires, yeah. We've got 4 things in the chat. Can you
Yeah, I don't-
questions in?
How do I do that? Check.
Okay, here's one. All right. Why don't you just scroll up a tiny bit, because I think we're missing a topic.
I
Okay.
can't even see the thing.
So Marwan's asking a question, very
Options.
operational focus, which is good. What about Haynes Index? Are we not using it anymore for categorizing atmospheric stability in accordance with FWI? Maybe useful for your training data sets too, for the ML?
Yeah. Machine learning.
Okay.
So did you read it out again, or do I need to?
Oh, no, that's fine. You go ahead.
Yeah.
I think I would have heard that. Yeah.
Okay, yeah, no, that's a good question. I actually did show the Haynes Index briefly, but I didn't talk about it on that plot, which had, I should throw it up again or not? I don't know if it's going to,
Maybe not.
yeah, so we use a different version. I think there's some work now being done saying that the Haynes Index itself is not great, and it was basically developed for the US and doesn't work in other parts of the world. So there's this so-called continuous Haynes Index, which was developed for Australia, which we're looking at to apply in Canada. And it seems to show some strength, some skill in helping with like the unstable convective environment I was talking about, that can drive fire activity. And we're also looking at the Showalter Index, and we're looking at lifted index, and we're doing a bunch of different indices. So yeah, so I hope that addresses that question. There we go. Okay.
Any questions from the audience? Yeah. Yes. You first, and then you at the back.
Thank you for that. So what is your prognosis for future forest fires in North America? We're just going to see more and more bigger fires.
Are we going to see more forest fires in North America in future? Sorry, just.
Yeah, no, that's good. Thank you. Yeah, that's a difficult question. That is, you sort of need a crystal ball to say that. We can say for sure that all the projections of fire weather, so all the trends that we're seeing so far and all the future projections are showing, because of climate change, all the climate models are showing extreme fire weather is going to be increasing over much of North America, right? So you expect if a fire does happen, that it'll burn under more intense conditions. So it might become a bigger fire, harder to contain. We have this term called burn severity, this metric, which is even though you have a certain area burned, how badly did it sort of, burn the vegetation in the area? So did it kill all the trees, or did it just kind of move through the surface and whatever? So there's this idea that we'll see a lot more severe fires. But then the problem is you can't really remove human behavior, and it's very hard to model human behavior going forward. So in fact, human caused fires are decreasing because fire management is getting more efficient at fighting fires. And also you can imagine if there's communities near where fires occur and there are people there, they can report them and they get to them much quicker, right? So there's this whole kind of interaction between human behavior and the fire regimes that we see, which is very hard to predict. And then there's forestry things, and then there's like what sort of succession, like when the big disturbance occurs, what is that forest replaced with? And there's all sorts of things which make it very hard to predict. That's why I just stick with fire weather, because it's getting worse. Yeah.
This heat dome, is there an obvious response by funding agencies to fire management to that kind of event, and that they change the way they're future planning, or is it just kind of accepted?
Yeah, there's been quite a bit of talk about prescribed burning. So prescribed burning is this practice where you basically put fire on the landscape yourself, because what you're trying to do is you're trying to emulate the sort of fire regimes we had pre-climate change, and you had a lot more smaller fires, and you create a mosaic. Rather than having a large continuous forest that can all burn down, you create a mosaic of burned and unburned areas, and so the fires you tend to get much smaller. So there's been a lot of talk around, should we be reintroducing prescribed burning? Because they did used to do it in British Columbia until the 1970s, and I think because when forestry industry really took off, they stopped doing it. So I don't know. I don't want to get into trouble by talking about the reasons for any of that. So I'll stay away from that. But there is talk of maybe we should be introducing more prescribed burning, for example. But then the other side of it is just can we predict these events so that we're better prepared to deal with them a few days to even weeks in advance. So but the fire agencies are putting out fires. It's not even an analogy or a euphemism in this case. That's what they're doing, and so they don't have time. Too busy putting out fires to often do some of the things that need to be done, I guess. And we can't blame them for that.
There must be quite a lot to learn from our Aussie neighbours in this respect, I guess, with because they do prescribe burning to remove some of the fuel, don't they, from the eucalypt?
Yeah, I don't know. Yeah.
I think they're so used to burning that that's an inherent property of eucalyptus, isn't it? And so they do prescribe burning to get rid of some of that fuel, I think, in some of those forests.
Yeah, well, in some countries there was an indigenous practice as well of burning, cultural burning, I think we call it in Canada. So there's the idea we should be doing more of that because it's exactly what prescribed burning basically is. Yeah, just.
Is it in those parts of North America, is the sort of native forest or the native vegetation more or less of a problem for a fire versus like those big forests? Because in Canada, I know there's a big forestry industry. Are those then human-made forests more flammable, more quickly? Is it?
Yeah, well, in Canada it tends to be the same. I might be wrong about this because I don't know much. I work for the Canadian Forest Service and know nothing about forestry. So, but I think in Canada, because there's a lot of pine plantations and there's a lot of pine there anyway, it may be more the distribution of the trees rather than the type of the tree being different necessarily. So I'm not sure, to be honest. But there are people working on, the difference between fire and plantations versus versus naturally occurring forests. So there's work being done on that.
Jen, one last question.
Do you use established climate cycles in your predictions like ENSO or Pacific Decade Oscillation?
Yeah, so I don't do seasonal forecasting myself. I'm just like trying to work on, you know, post-processing the models, or whatever. But the people that I work with that do seasonal forecasts for the public and for fire managers, they look at all of those things. They look at the teleconnections, they look at sea surface temperatures, drought conditions, you know, snow melt, all of those things that they've got a handle on at the beginning of the season, and they try to predict, you know. Yeah. So we have meteorologists that do these things.
And there's another question there, Jane.
Another question. Okay, thank you for the talk. Really interesting. Last week there was a study published in Nature on Australian wildfires injecting ozone depleting substance into the stratosphere via aerosols. These then contribute to ozone loss. They only looked at the Australian case. Do you think this could also be happening in the Arctic?
Yeah, I don't know. In the Arctic, problem is we don't really have a handle on fire in the Arctic. In fact, that's some of the work we're trying to do, because a lot of the fires are low intensity and they're hard to observe with the sort of satellite resolution that we have now. So, for example, there's a lot of peatland and tundra up there, which can have a huge impact on carbon accounting and so forth, but we don't really have a great handle on how much fire is occurring on the landscape, and so it's hard to ask that question. Also, I don't know that much about that question.
So Pete can one question, yes, sure, type it up. Because peat is basically like a fuel in itself, and it can just
it burns
smolder.
underground, yeah,
Smolder,
it
smolder.
smolders, and in fact, snow, it can be snow on the ground, and the fire is still basically dormant underground. So we call them holdover fires. The media call them zombie. So everyone likes songs.
How fast are you at typing?
It's pretty fast.
Did you find any anomalies in the burnt area then correlating with FWI? I'm asking because some of us are interested in how local topography can modulate fire behaviour at the mesoscale, so daily and sub-daily timescales. Anything interesting in the anomalies of your study?
Yeah, well, I mean, I think I showed that plot. There was larger anomalies in FWI and other fire instances on those spread days, and those spread days you'll have, those are the days that cause more area to burn on the fire spread days. So I think if you correlated just the burned area, you'd see something similar, maybe not quite a strong signal as the spread days. But.
Excellent. Sounds like you're really interested, Marlon. So maybe you should come over, and if you're in at Otago, come and visit Piyush. I'm sure he'd love to have a chat with you. Anyway, thank you so much. That was absolutely fascinating. Really, really enjoyed it. And please join me to thank Piyush.